You're listening to DTFHN for July 29th, 2026. I'm your lovingly jailbroken host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where mass nostalgia and raw engineering share a single comment thread. Today is all constraints and stubbornness. People building things that shouldn't work on hardware that shouldn't matter. Strap in. What's the weakest computer you'd trust with network access? Not a Raspberry Pi. Those are practically workstations now, not your old phone collecting dust in a drawer. I'm talking about a Kindle, an e-reader with an e-ink screen that refreshes like it's thinking really hard about whether it wants to. A device Amazon built to do exactly one thing: sell you books. And a community of tinkers looked at it and said, you know what this needs? A full mesh VPN. And they built one. Run this forward for a second. Mitanshu Sukwani writes a Tailscale implementation for jailbroken Kindles. It works, kinda. Your Kindle shows up on your tailnet with a green dot. You can SSH into it, but it's running in user space mode because the Kindle's kernel doesn't expose the TON interface. So your Kindle can be reached, but it can't reach back. It's like giving someone a phone that only receives calls. Then Greywolf Wasser Joser comes along and builds a Kale extension that adds proxy mode. SOX 5 and HTTP Connect, listening on localhost port 1055. Now KO Reader, which, by the way, is itself an open-source replacement for the entire Kindle reading interface. KO Reader can route through Tailscale's daemon to hit your Calibre server, your Wallabag instance, your self-hosted RSS feeds. Your e-reader just became a thin client for your entire personal infrastructure. The comedy here is in the engineering constraints. This is a device with the processing power of a moderate calculator. The screen updates are measured in fractions per second, not frames. And people are setting up SSH sessions through it with Bluetooth keyboards using the KTerm app. Is that practical? The Tailscale team themselves admit. Not really, but they wrote about it anyway because builder culture doesn't ask permission from the practicality committee. And on some Kindles, there's even a full TON mode now. Device-level networking. The whole stack, running on hardware that Amazon designed to be a lockdown content delivery terminal. This is what I love about open source in the wild. Amazon ships a device with one purpose and a locked bootloader. The community jailbreaks, it replaces the reading software, adds mesh networking, and turns it into a node on your personal network. One person writes the Tailscale client. Another writes the proxy layer. A third builds a KO Reader plugin that works on Kindles, Kobos, and pocketbooks. Nobody asked for a business case. Nobody filed a product requirements document. They just shipped code because the problem was interesting. The tools exist. The kernel might not cooperate, but there's a workaround for that too. There's always a workaround when the source is open. Moving on. Trash'em1, that's the name of an assembler. Someone took Asm1, which was itself a fork of Seca, which was itself based on a commercial product, and they hacked it, renamed it Trash'em1, and passed it along. The author of this article notes that the resulting family tree of assembler forks rivals that of Unix systems. That detail deserves more attention than it gets. Because here is the question. Nobody in the Damascene nostalgia's conversation seems to ask, what do you call a community that builds its own tools from scratch, forks them freely, shares the modifications without licensing agreements, and iterates across decades? All without ever using the phrase open source. You call it the thing that open source always was before anyone branded it. The Demoscene emerged in the 1980s. Teenagers on Amigas and Commodore 64s writing assemblers, trackers, rippers, sine table generators. Every tool in this article was built because someone needed it, and nobody was selling it. Or because what was being sold wasn't good enough. Elite Sinus Producer generates lookup tables so a 7 MHz CPU can fake complex math in real time. Multi-Ripper hunts through memory for music samples and sprites left behind after you quit a game. Fast Tracker 2 became so intuitive that people in the comments still remember the physical sensation of using it decades later. These tools are strange. The help screen for Elite Sinus Producer flashes between red and cyan while displaying text in a font optimized for everything except reading. The interfaces are dense, idiosyncratic, sometimes hostile. None of that matters. What matters is that they were shared, modified, passed hand to hand on floppy disks and bulletin boards. The entire culture ran on the assumption that if you built something useful, other people should be able to use it, break it, rebuild it. This is builder culture at its most unself-conscious. No manifestos, no foundations, no conference talks about community governance. Just people making tools because the tools needed to exist and giving them away because hoarding them never occurred to anyone as a serious option. The Demoscene is still active. People are still writing size-coded demos in 4 kilobytes, still building custom tool chains, still sharing everything. The tools look different now, but the architecture of the community hasn't changed. It was open before open had a logo, and the work it produced, the art, the music, the code, stands as quiet, permanent proof that the best tools come from people who build for each other, not for shareholders. So what happens when that same build for each other energy meets the unglamorous but critical world of software specs? Story 3, SpecForge. Formal verification has a reputation problem. It's the thing everyone agrees software needs and almost nobody actually does. The tools are too academic, too disconnected from where code gets written, too much ceremony for too little payoff. SpecForge is a direct answer to that gap, and the interesting part isn't the theory. It's the delivery mechanism. Lilo is a temporal specification language. You declare signals, time-varying values, like temperature or humidity. And then you write specs against them using temporal operators. Always, eventually, historically, past. These aren't decorative. Always phi means phi holds at every future time step, eventually with a bounded interval. Say eventually 0 to 10 means it becomes true within 10 time units. You're writing math that tracks how a system behaves across time, which is exactly what matters for anything physical or safety critical. Take the recovery spec from their example. It says, always, if an emergency condition fires, then eventually within 10 time units, temperature returns to normal range. That's a single line of Lilo. Writing that same requirement as a prose document gives you ambiguity. Writing it as test cases gives you coverage gaps. Writing it as a formal spec gives you something a machine can check exhaustively. Now follow the design decision to its logical extreme. If specifications are first-class artifacts, not comments, not documentation, but executable, analyzable objects, then the tooling has to live where engineers already work. SpecForge ships as a VS Code extension. You get syntax highlighting, type checking, satisfiability analysis, all in line. You can monitor recorded behavior against specs, generate example traces, search for counterexamples, export to other formats, animate behavior over time. There's a Python SDK for Jupyter notebooks. The specs aren't locked in an academic tool that 3 people at your company know how to run. They're in the editor, in the notebook, in the workflow. This matters because formal methods have failed adoption for decades. Not because the math was wrong, but because the interface was wrong. The knowledge was trapped behind tool chains that demanded you leave your environment, learn a separate ecosystem, convince your team to add a build step nobody understood. SpecForge treats that as the core engineering problem. The specification language is expressive enough to capture real temporal properties of hybrid systems, and the tooling is ordinary enough that someone already using VS Code can start writing specs without a PhD in model checking. The platform is versioned, documented, available. The specs are readable. The analysis runs locally. That's the architecture of a tool built to be used, not to be cited. Tools that run locally and respect your workflow. Pause. That principle scales all the way down to your database. Story 4. SQLite in production. Optimizing WAL Mode, Concurrency, and VFS Layers. I once spent 3 days debugging a microservice that was slow for one reason. Network round trips to a database sitting 6 milliseconds away. 6 milliseconds sounds like nothing until you multiply it by every query in every request. We ripped it out, dropped in SQLite, and watched P99 latency fall off a cliff. That experience rewired how I think about where data should live. So, let me play the other side for a moment. The conventional argument against SQLite in production is concurrency. One writer at a time. No replication, no failover. And honestly, if you're running a traditional multi-server deployment, that argument holds. But here's where the engineering gets beautiful. The conventional argument assumes a conventional architecture, and the architecture has moved. Write-ahead logging is the mechanism that makes this work, and it deserves more respect than it gets. In the default rollback journal mode, a SQLite copies original database pages to a journal before writing. Writes block reads, reads block writes. It's safe, it's simple, and it's completely wrong for a production workload. WAL Mode flips the model. New transactions append to a separate WAL file while readers continue hitting the main database. Readers and writers stop blocking each other. That single pragma statement, journal mode equals WAL, transforms SQLite from a single-threaded embedded database into something that can genuinely serve concurrent traffic. The subtlety is in checkpointing. The WAL file grows as writes accumulate, and periodically those pages need to merge back into the main database. SQLite gives you 4 strategies, and your choice determines your latency profile. Passive checkpointing never blocks anything, but might leave work undone. Full checkpointing guarantees completeness, but stalls new writes. The craft is in matching the strategy to your workload. And this is where most teams either over-engineer or never tune at all. The comments on this piece are worth noting. Several readers flagged it as AI-generated, which, there. But the underlying technical content maps to real, well-documented SQLite internals. The more interesting pushback came from engineers asking about replication and failover. Tools like LiteFS exist precisely for this. The ecosystem is growing because the demand is real. What I admire here is the architecture itself. SQLite is public domain, not MIT, not a PAC. Public domain. Anyone can read it, modify it, embed it. The entire database is a single file. The source code is a single amalgamation. That's a design philosophy that trusts the developer completely. NVMe storage, eliminated the disk bottleneck. WME storage eliminated the disk bottleneck. WAL eliminated the concurrency bottleneck. What's left is a database that runs in your process, answers queries in microseconds, and belongs to everyone. The tools exist. The tuning is documented. The rest is just building. Software that belongs to everyone. That's a thread that runs all the way back to the oldest languages still alive. Story 5. Lisp moving, Forth moving Lisp. Make the case against these languages. Go ahead. Forth is a relic from 1968 that looks like someone typed random words separated by spaces. Lisp is parentheses all the way down. Neither one has a package manager worth mentioning. Neither one will get you hired at a fine company, and the communities for both fit comfortably in a mid-sized conference room. Modern languages have types, tooling, ecosystems, jobs. Why would anyone waste time implementing one dinosaur inside another dinosaur? That argument sounds reasonable right up until you ask a different question. Why can Forth be implemented on virtually every programmable computer ever created? Why has Lisp survived 60-plus years of languages supposedly replacing it? The answer is the same for both, and it has nothing to do with nostalgia. Doug Hoyt's over Lambda dedicates an entire chapter to building Forth inside Lisp using macros. And the exercise reveals something the modern tooling argument completely misses. These languages aren't products. They're architectures. Forth doesn't need a corporation maintaining it because the entire language fits in your head and on your hardware. Chuck Moore created it in 1968 with no government grant, no university lab, no corporate sponsor. He needed to solve problems in astronomy and hardware design. So he built a language that could run anywhere he needed it to run. That's not a limitation. That's a design philosophy that refuses to create dependencies. Pull this through the bootstrapism lens, and the picture sharpens. Every language backed by a major institution carries that institution's priorities baked into its DNA. Fortran served IBM's customers. C served AT&T's operating system. Common Lisp eventually got DARPA money and accumulated the complexity that comes with it. Forth stayed independent and stayed minimal. Anyone could implement it. Anyone could modify it. The latter stayed where people could reach it. What Hoyt demonstrates by weaving Forth into Lisp is that two languages designed around extensibility can merge without either one breaking. Lisp macros become Forth's metaprogramming. Forth's stack discipline becomes a Lisp abstraction. Neither language needs permission from the other because neither language was designed to gatekeep. One commenter called writing Forth programs brittle, like glass sheets. Fair. But glass is also transparent. You can see every single thing happening in a Forth program. No hidden runtime, no framework magic, no abstraction you can't peel back. The fragility is the flip side of total visibility, and total visibility is what you get when nobody's trying to sell you a black box. The tools exist. They've existed for decades. They belong to everyone. Total visibility matters even more when code is writing code FOSS, which brings us to keeping AI-generated code honest. Half your weekly pro plan usage gone. One scan on a small repo, running for almost an hour before it got interrupted. That's what one user reported after pointing Codex Security at their code base. OpenAI's new open-source security scanner, freshly released, hungry for compute, and apparently not shy about eating your quota to do its job. The tool itself is straightforward, a CLI and TypeScript SDK that scans repositories for security vulnerabilities, validates findings, suggests fixes. npm install, login scan, the kind of developer experience that's genuinely well-crafted. And credit where it's due. The engineering team includes people from PromptFu, which is one of the better open-source AI evaluation frameworks out there. These are builders who know what they're doing. But let's run the architecture check. Codex Security is open source. The code is on GitHub. You can read it, fork it, modify it. That's real. And then you look at authentication. It phones home to OpenAI. Your scans run against their API. Your code base gets sent to their infrastructure. The CLI is open. The engine behind it is closed. You're reading the menu, but the kitchen is behind a locked door. One commenter put it perfectly. Security tools from AI companies feel like fire departments run by arsonists. That's sharp, maybe unfair, but it names the structural tension. OpenAI wants to secure your code using the same class of models that introduced an entirely new category of vulnerabilities into software development. The company that can't keep its own systems from leaking wants to audit yours. Now, the Promptful folks working on this are genuine security people. The tool will probably get good. Open sourcing the CLI is a legitimate first step. But the question isn't whether the scanner works. It's what happens when OpenAI changes the objective function, when the API pricing shifts, when the model behind the scanner gets deprecated or paywalled or bundled into an enterprise tier you can't afford. A security tool you depend on but don't control is a liability dressed as an asset. The scanner that eats half your weekly compute budget on a single run is telling you something about where the power sits in this relationship. The good news: the code is out there now. Someone will fork it. Someone will plug in a local model. Someone will build the version that doesn't phone home. That's how open source wins. Not because the corporation intended it, but because they couldn't stop it once the code was public. Moving on. Every browser tab is a context switch, and context switches are where attention goes to die. Here's the setup. You're on Hacker News. You see an interesting link. You click the article, you read it. Then you think, wait, what did the comments say? So you go back, or you'd already opened the comments in a second tab, and now you're bouncing between two tabs, like a tennis ball in a rally that never ends. Multiply that by 30 stories a day, and you've invented a small, personal hell of tab management. Someone got tired of it and wrote a user script. Every new here, about as simple as software gets. It detects when you're reading an article that has a Hacker News discussion, pulls the comments via the Algolia Search API, and slides them into a resizable sidebar right next to the article. No extension store approval process. No permissions dialogues asking to read your browsing history. Just a JavaScript file you paste into TamperMonkey or ViolentMonkey and forget about. The analogy I keep coming back to is sous vide cooking. You take two things that obviously belong together, protein and heat, and instead of making you mange them separately, switching between stove, top, and oven, checking temperatures, you just put them in the same sealed environment and let physics do the work. Doan here does that for reading and discussion. Same window, same context. The article is the protein, the comments are the heat. Together, they're the meal. And the comments on this one are predictably great. Someone points out that the Hacker News discussion often refutes the article's main point, which is exactly why you want both visible simultaneously. Another person built a similar Firefox extension. A third asks about bookmarklets. This is builder culture doing what it does. Someone scratches an itch, ships it under MIT, and immediately 5 people show up with variations and improvement. The whole thing is maybe 200 lines of JavaScript, no build step, no framework, no dependency tree that would make a arborist weep. Just a user script that does one thing well, published where anyone can read it, fork it, improve it. The tools exist. They're small, they're free, and they're yours to modify. That's the whole point. Now, completely different energy here. More craft, Story 8, Substack writers. You need a website. In Iowa, America Online had 20 million subscribers and a walled garden that felt like the entire internet. Writers published on AOL keywords, businesses built storefronts inside AOL's ecosystem. The pitch was identical to what we hear today. Built-in audience, easy tools, no technical overhead. Then AOL's business model shifted, and millions of people discovered that everything they'd built existed at the pleasure of a corporation that had just changed its mind. This article from Elizabeth Tai is making the same argument people have been making since GeoCities, since Tumblr, since Medium. And the reason people keep making it is because it keeps being right, and writers keep not listening. The core insight is simple. When your writing lives at your name, Substack.com, Substack owns the infrastructure, the URL, the discovery mechanism, and the relationship with your reader's inbox. You are not building equity, you are generating content on someone else's land. The article uses the term digital sharecropping, which is blunt but historically precise. What's more interesting is the solution she proposes. Posse. Publish on your own site. Syndicate elsewhere. This is an indie web principle that's been around for over a decade, and it's exactly the right architecture. Your website is the canonical source. Substack, or whatever replaces Substack in 3 years, becomes a distribution channel. You get the audience without the dependency. One of the comments nails something the article doesn't fully develop. Someone built their blog with Codex and Cloudflare, writing in Markdown, publishing with a static site generator, owning every byte. Another commenter mentions Leaflet, which connects publishing to the open social ecosystem. These aren't hypotheticals. The tools exist right now, and they're simpler than they've ever been. The pattern from computing history is unambiguous. Centralized platforms consolidate, then extract. CompuServe did it. AOL did it. Facebook did it. The only content that survives these cycles is content that lives on infrastructure you control. A domain name costs $12 a year. A static site generator is free. The math is not complicated. Your words deserve an address that doesn't have someone else's name on the lease. This one is pure joy. What does it actually cost to make a computer display a single pixel of color? Today, the answer is essentially nothing. Your GPU pushes millions of polygons without breaking a sweat. But in 1985, every pixel was a negotiation between hardware and imagination. The Commodore Amiga solved this negotiation with custom silicon. 3 chips named Agnes, Denise, and Paula. That could do things no personal computer had done before. Hold and modify mode gave you 4,096 simultaneous colors on screen when the Mac was still monochrome, and the IBM PC could manage maybe 16 colors if you were lucky. The Amiga didn't achieve this through raw power. It achieved it through clever architecture, planar graphics, copper lists that could change the color palette mid-scanline, a blitter that moved memory around without bothering the CPU. Every trick was an engineering answer to a resource constraint. The Amiga Graphics Archive collects the visual output of that era. Pixel art, Damason Productions, game graphic, all made within those constraints, and the work is stunning. Artists operating with palettes of 32 colors or fewer produced images with a richness that feels almost impossible given the limitations. This wasn't a compromise. It was a discipline. When you have 64 kilobytes of chip RAM and a 320 pixel wide display, every byte carries meaning. You learn what a color palette actually does. You learn what dithering is for. You understand, at the hardware level, how a screen becomes an image. The archive itself matters because this knowledge evaporates. The techniques Amiga artists developed and optimized copper lists, sub-pixel tricks, palette cycling animations that simulated motion without animation frames. These are computational ideas expressed in art. They belong in the commons where anyone studying computer graphics can reach them. A 16-color portrait that reads as photorealistic from 3 feet away teaches you more about human visual perception than a semester of shader programming. The constraints are gone now. The knowledge shouldn't be. Someone archived it, and the URL is free to visit. That's the whole mechanism. Preserve the work, keep the door open. Now for something completely different. Someone got Half-Life running on macOS 9, and honestly, that's the kind of unhinged dedication I live for. One name in the credits tells you everything. Dr. Shea. A single GitHub handle attached to a fork of an open-source engine called Zash3D-FWGS, which is itself a cleanroom reimplementation of Valve's GoldSec engine. That reimplementation has existed since 2011. 15 years of quiet, cumulative engineering by people who wanted a first-person shooter engine to belong to everyone. And now it runs Half-Life on a PowerPC Mac from 19999. Pull this thread for a moment. Valve planned a Mac OS 9 port back in 1999 through Logicware. It got killed at the last minute in one of gaming's more frustrating cancellations. Valve themselves didn't bring Half-Life to any Mac until 2013 on Intel hardware. Running OS X. The original PowerPC promise just evaporated. 28 years of nothing. Then one developer forks an open engine, targets a dead platform, and ships the entire Half-Life catalog. Base game Blue Shift Opposing Force multiplayer, the uplink demo. Playable start to finish on a G3 iMac with Mac OS 9. The machine needs 8 megabytes of VRAM to run comfortably. 8 megabytes. That constraint forces you to understand every byte crossing the bus, every texture swap, every draw call. The engineering discipline required to hit that target is genuinely beautiful work. Now run this forward. Zash3D FWGS is open. Its architecture is portable. Dr. Shea proved you can retarget it to a platform Valve abandoned a quarter-century ago. Imagine the same approach applied to every engine that's ever been open-sourced or re-implemented. At Tech, Bill, Open, MW, every platform that was declared obsolete becomes a viable target again. The hardware doesn't expire. The software gatekeeping is what expires it. A corporation canceled the port. The community finished it. That's the mechanism. Open the engine, publish the code, and someone with enough craft and stubbornness will carry it the rest of the way. The tools were sitting there since 2011. All it took was one person who decided a 28-year-old promise was still worth keeping. This has been your daily tech feed for Hacker News for July 29th, 2026. This podcast is entirely AI-generated. Scripts by Claude Sonnet 4.7. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something small and give it away. We'll see you back here tomorrow.